Okay, this is the last lesson. It's from Unit 8, Chapter 11, Permutations, Combinations, and the Binomial Theorem. We're going to look at the Binomial Theorem. We're going to look at Pascal's Triangle and combinations and how it relates to the Binomial Expansion. This is Section 11.3 in your text. And as I said, the focus now is going to be on relating the coefficients in the expansion of x plus y to the n, where n is an element of the natural numbers, to Pascal's triangle, and the combinations. We're going to be looking at expanding x plus y to the power of n in a variety of ways, and we're going to be determining a specific term in the expansion, x plus y to the power of n. Okay, the first thing we need to do is talk about Pascal's triangle. You should recall what Pascal's triangle looks like. Pascal's triangle is simply a series of numbers forming a triangle. And you can see here, based on the triangle, that all we're doing in Pascal's triangle is we're simply adding the two previous numbers above a specific number to get the next number. What I mean by that is this. We start with 1, then we go 1, 1. Then we simply add, and we continue to expand. The outside numbers will always be 1 along Pascal's triangle. So all of these numbers out here will always be 1, 1, 1, 1, and 1. Now the inside numbers are formed by adding the previous numbers above them. So 1 plus 2, for example, is 3. To get the number here in Pascal's triangle, we do 2 plus 1, which is 3. And so on. 1 plus 3 is 4, so we add the two numbers above to get the number below. This number here is formed by adding 3 and 3 to get 6. 3 plus 1 is 4, and so on. 4 plus 1 is 5. 4 plus 5 is 10. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is again 5. So these are the numbers that form Pascal's triangle. And of course it continues on with more and more rows in the triangle. Okay, let's see how that's related to the expansion of x plus y to the power of 4. X plus y to the power of 4, when expanded, looks something like this. X plus y times x plus y times x plus y times x plus y. If you were to multiply this out, it becomes very complicated and very easy to make a mistake. But let's just go through the process quickly. X plus y times x plus y is x squared plus 2x, y plus y squared. X plus y times x plus y is also, again, x squared plus 2x, y plus y squared. Now multiplying these two together, of course we need to multiply every term by every other term. And when we multiply those out, you will get this. Simplifying, you will get this. So x plus y to the power of 4 becomes x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the power of 4. Again, I didn't really talk a lot about this, but you know you're multiplying each term by every other term to get this expression. Now, if we were to focus on the coefficients of this expansion, can you find the coefficients of the terms in the row of Pascal's triangle? If you look at the coefficients, they are 1, 1, 4, 6, 4. So the coefficients are again 1, 4, 6, 4, 1. If you look at the coefficients, they do exist in Pascal's triangle. They exist in row number 5. This is the 5th row in Pascal's triangle. If you look at the 5 numbers here, they are exactly the coefficients that exist here. If you were to focus on the exponents, is there a pattern in the exponents? And if you look closely, there is. We have an x to the power of 4, an x to the power of 3, an x to the power of 2, an x to the power of 1, and I suppose an x to the power of 0. So the powers of x continuously decrease, starting with x to the power of 4. What about the powers of y? I got a y to the 1, a y to the 2, a y to the 3, and a y to the 4. And if you think about it, I guess a y to the 0 can also fall into this location here. So I start with y to the 0, which of course is 1, y to the 0, y to the 1, y to the 2, y to the 3, y to the 4. So there is a pattern as well with the exponents. We got the x's are the powers decrease. Decrease by 1. starting with 4. And the y's, the powers actually increase by 1, starting with 0. That's the pattern that exists there. X to the power 4, 3, 2, 1, 0. Y to the power 0, 1, 2, 3, 4. And notice again that the coefficients are indeed the numbers in Pascal's triangle. So that's pretty interesting, I think. The binomial expansion, x plus y to the power of 0, x plus y to the power of 1, 2, 3, and 4, are actually very closely related to Pascal's triangle. And if you look at the numbers in Pascal's triangle, we got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And again, notice that x plus y to the 0 is 1. That is your first row. The second row is x plus y to the power of 1. 1 and 1. There are your coefficients, x to the power of 1, y to the power of 1. Really, I could write in here y to the 0, x to the 0. I'm starting with x to the power of 1, y to the 0. I decrease my powers of x by 1, I increase my powers of y by 1. The same is happening here. Look, x plus y squared. Look at the coefficients, 1, 2, 1. I start with x squared, y to the 0. I decrease my values of powers of x, by 1. I increase my powers of y by 1. X squared, x to the 1, x to the 0. I increase my powers of y, starting with y to the 0. 0, 1, 2. Same is true here. X cubed, x squared, x to the 1, x to the 0. Starting with my y, y to the 0, y to the 1, y to the 2, y to the 3. But again, look at your numbers. 1, 3, 3, 1 are formed as the numbers in Pascal's triangle. X plus y to the 4, you just saw me do it. X to the 4, y to the 0. Decrease your powers of x by 1. Each time, increase your powers of y by 1, starting with y to the 0. And of course, over here, we get an x to the 0. But notice again, it's the fifth row in Pascal's triangle. X plus y to the power of 4 is actually the fifth row in Pascal's triangle. So if we want to expand, delete that. If I want to expand here, x plus y to the power of 5, you should recognize now that x plus y to the power of 5 is going to be the next row in Pascal's triangle. So the coefficients will be 1, 5, 10, 10, 5, and 1. So x plus y to the power of 5. It will be 1. Start with your power of x, which is your x to the 5. The best way to do this now is to simply do this, okay? 5. Right, let's write out all the coefficients first. Now let's decrease our powers of x by 1. X to the 4, x to the 3, x to the 2, x to the 1, x to the 0. I'm going to write it in there. Now let's increase our powers of y, starting with y to the 0. Y to the 4, and finally y to the 5. There is the expansion of x plus y to the 5, and we're using Pascal's triangle to do that. X plus y to the 7 will be the 8th row in Pascal's triangle. So let's figure out what the 8th row in Pascal's triangle looks like. Well, the 6th row will be 1, 6, 15, 20, 15, 6, and 1. And I need to do one more row. It's going to be 1, 7, 21, 35, 35, 21, 7, and 1. And again, I need to write that out now with the expansion of x plus y to the 7. So we start with 1, x to the 7, y to the 0. I'll do each one at a time now. Plus 7, taking my second coefficient, 7. Decrease your powers of x by 1, increase your powers of y by 1. 21 x to the 5 y squared, 35 x to the 4th y cubed, plus 35 x to the 3 y to the 4, plus 21 x squared y to the 5, plus 7 x y to the 6, plus 1 y to the 7. And there's the expansion of x plus y to the power of 7. So again, we're relating Pascal's triangle now to a binomial expansion of x plus y to the power of n. What is the expansion of x plus y to the power of 5? I think we just did that one. Back here, yes we did. So I won't bother to do that example because I've already did that. X plus y to the power of 5. I didn't realize it was actually already done, or I wouldn't have put it here as example 1. But I'll just say refer to previous slide, because I just did that one. We don't need to do that again, of course. Okay, let's move on here. The coefficient of the binomial expansion can also be determined using combinations. It's interesting that the numbers in Pascal's triangle are actually these numbers that you see here. The C of 0 choose 0 is 1. The C of 1 choose 0 is 1. The C of 1 choose 1 is 1. These numbers coincide. The C of 2 choose 0 is 1. The C of 2 choose 1 is 2. The C of 2 choose 2 is 1, and so on. 3 choose 0 is 1. 3 choose 1, 3. 3 choose 2, 3. 3 choose 3, 1. Notice how we're increasing here by 1. All of these values are increasing by 1 each time. Notice again now that this is the first row, second row, third row, fourth row, fifth row. But this one is actually a little easier to use because this is the expansion for x plus y to the power of 4. We don't have to think about the next row anymore. This is much nicer to use for expansions than Pascal's triangle because they're pretty simple to come up with because it's exactly with the power. And you'll see what I mean by the next example. Expand x plus q, p plus q to the 6 using combinations. So using combinations, here's how it looks. P plus q to the power of 6 is going to be, I'm going to write out all your coefficients first. It's the C of 6 choose 0. And again, note the 6 here, and that's what I start with, the C of 6 choose 0. I don't have to worry about whether it's not row 5, row 6, row 7. It starts with 6 because my power is 6. C of 6 choose 0 is my first coefficient. My next coefficient is 6 choose 1. My next coefficient is 6 choose 2. My next coefficient is 6 choose 3, and so on. Right on up to the C of 6 choose 6. Oops, should get a little more room here, I guess. And the final one there is the C of 6 choose 6. Now we do the exact same thing again. We start with P to the power of 6, and we reduce our powers by 1. So I'm just going to write out all my P's now, just to show the pattern here. And of course, I start with Q, and I start with Q to the 0, and I increase by 1. Q to the 6. Now let's simplify. The C of 6 choose 0, do that on your calculator. The C of 6 choose 0 is 1. So I got 1, P to the power of 6. Plus the C of 6 choose 1 is 6, P to the 5, Q. Plus the C of 6 choose 2, I can do that on my calculator. So 6, math, go over to probability, go down to the C of n choose R. 6 choose 2 is 15. 15. P to the 4, Q squared. Plus the C of 6 choose 3. Do it again on your calculator. C of 6 choose 3. Oops, I made an error. And you get 20. 20. P3, Q3, plus the C of 6 choose 4. The C of 6 choose 4 will be the same as the C of 6 choose 2. It will be 15. P squared, Q to the 4. C of 6 choose 5 is the same as C of 6 choose 1, which is 6. P1, Q to the 5. And the C of 6 choose 6 is 1. P to the 0 is 1. Q to the 6. There's the expansion using combinations. I want you to notice the pattern in the coefficients as well. 1, 6, 15, 20. Once it starts to go down again and you get the same number, the pattern continues. So notice that it's a 15, 15, 6, 6, 1, 1. Once you get the number in the middle and the pattern starts to go down again, you can just repeat the numbers on each side. Okay, identify the patterns that exist in the expansion. Now, let's look at the patterns that exist. Clearly, the coefficients have patterns. Clearly, the coefficients involve the patterns to C of 6 choose 0, C of 6 choose 1, and so on, right on up to the C of 6 choose 6. But there are other patterns that exist in this expansion. I want you to look closely at this power and this power. This power here is 6 subtract 0. This power here is this number. It works every time. 6 subtract 1 is 5, Q to the 1. 6 subtract 2 is 4, Q to the 2. 6 subtract 3 is 3, 3. 6 subtract 4 is 2, 4. 6 subtract 5 is 1, 5. 6 subtract 6 is 0, 6. So there's a pattern that exists as well with my powers. And it's associated with these numbers. This first power will be the difference of these two numbers. Your second power will be equal to the second number. That's a very important pattern, because we can use that pattern to help us find an exact term in an expansion. In fact, this is how we do it down here. Anyway, here is your binomial theorem to expand any power of a binomial expansion. A plus b to the power of n can be written as the C of n choose 0. You always start with the C of n choose 0, and you end with the C of n choose n. And again, we increase C of n choose 1, C of n choose 2, C of n choose 3, and so on, right on up to the C of n choose n. Notice again your powers here. N subtract 0 is n. N subtract 1 is your power. N subtract 2 is your power. N subtract 1 is 1. N subtract n is 0. Your second power is this number. 0, 0, 1, 1, 2, 2, and n. Very important statement here. You can determine any term in the expansion of x plus y to the n using patterns without having to perform the entire expansion. The general term, the t of k plus 1, has the form of the C of n choose k, x to the n subtract k, like I just told you, these two numbers subtracted, y to the k. For example, if you're asked to find the fourth term in this expansion, you need to think about the fourth term in the expansion. The fourth term will be the C of 7 choose 0 is the first term, the C of 7 choose 1 is your second term, the C of 7 choose 2 will be your third term, the C of 7 choose 3 would be your fourth term. This is the fourth term here, the C of 7 choose 3. So if I'm looking for the fourth term, the C of 7 choose 3 is simply x to the power of 7 subtract 3, y to the power of 3. The C of 7 choose 3 is 35, x to the power of 4, y to the 3. You're going to see me do another example or two of that. Here we go. What are the coefficients of the expansion C plus d to the power of 5? Only looking for the coefficients here. It's going to be C, 5 choose 0 will be your first coefficient. C of 5 choose 1 is going to be your second coefficient. The C of 5 choose 2. The C of 5 choose 3. The C of 5 choose 4. And the C of 5 choose 5. There are your 6 coefficients for the expansion C plus d to the power of 5. You always start with 0. You end with your power here. And you start with your power here. How many terms are in that expansion? Well, you can see that there are 6 coefficients, so there are 6 terms. Starting with 0, going to 5. What is the simplified expression for the second term in the expansion? If the terms are written as descending powers of c. The second term in the expansion. Think about this now. The second term is a c of 5 choose 1. If I use what I just explained to you a minute ago, the c of 5 choose 1 times c to the power of 5 subtract 1 times d to the power of 1. Notice my powers again. I subtracted these two numbers, and the second power is that number. The c of 5 choose 1 is 5. C to the power of 4, d to the power of 1. There's the second term in that expansion. We'll do a couple more examples here. Use the binomial theorem to expand. Now notice your expansion this time is not a and b or x and y. It's 2a subtract 3b. But we treat it the exact same way. The first thing I got to do is rewrite this as 2a plus a negative 3b to the power of 4. Because I want to make it look like x plus y to the power of 4. But of course, rather than an x now I got a 2a, rather than a y I got a negative 3b. But I do it the exact same way that I did the others. I simply start with the c of 4 choose 0 plus the c of 4 choose 1 plus the c of 4 choose 2. These are my coefficients. Plus the c of 4 choose 3 plus the c of 4 choose 4. Now I need to put in my terms. The first term is 2a to the power of 4 subtract 0, which is 4. My second term is a negative 3b to the power of 0. Again, note 4 subtract 0 is 4. That 0 goes right there. I do the next one. It's simply 2a to the power of 4 subtract 1, which is 3, and I'm decreasing by 1 if you want to look at it that way, times a negative 3b to the power of 1. 2a to the power of 2, negative 3b to the power of 2. I have here 2a to the power of 1, negative 3b to the power of 1 as well. And of course, the last one is going to be 2a to the power of 0, negative 3b to the power of 4. I need to simplify each of these terms now and see what I end up with here. Okay, the c of 4 choose 0 is 1. I don't need to do a calculator, I know that. The c of 4 choose 0 is always going to be 1. 2a to the power of 4 is 2 to the power of 4, which is 16, a to the power of 4, times 1. Anything raised to the power of 0 is equal to 1. Plus, the c of 4 choose 1 is 4. 2 cubed is 8, a cubed, negative 3b. Plus, the c of 4 choose 2, I think it's 6, but I'm just going to double check here. The c of 4 choose 2 is indeed 6. 2a squared is going to give me 4a squared times a negative 3b squared is going to give me a positive 9b squared. Plus, the c of 4 choose 3 is 4. 2a times a negative 3b plus the c of 4 choose 4 is 1 times a negative 3 to the b to the power of 4. Negative 3 to the power of 4 is 81, b to the 4. And let's finally write the final answer here. I got 16 a to the 4 plus, oh, it's actually a minus, isn't it? I got 8 times 4 times a negative 3b times, of course, my a squared, a cubed. So let's just get my numbers here. 4 times 8 times a negative 3, and I get a negative 96. So I get a negative 96 a cubed b plus 4 times 6 is 24 times 9. It's 216. 216 a squared b squared plus 4 times 2 is 8 times a negative 3 is a negative 24, so I guess I can make this subtract here. plus 81 b to the power of 4. I want you to notice that there's still a pattern that exists in my powers. A to the 4, a to the 3, a to the 1, a to the 0. Sorry, I must have left out an a to the 1 here because I don't have it in there, and I need, see, I'm looking for the pattern. There will always be a pattern left with your powers. So I've noticed now I've made a mistake here. A to the 4, a to the 3, a to the 2, a to the 1 should be there, a to the 0. And there's my mistake. I left out the a. So let's put it in. So you can easily check and see if there's still a pattern. It doesn't have to be the exact pattern that I just identified. Sometimes your values of a decrease by 2 or decrease by 3. It's not always by 1 in this case now. But I saw that I had an error here. And again, the pattern with the powers b to the 0, b to the 1, b to the 2, b to the 3 should probably be here somewhere. So that means that I've made a mistake here as well. B to the power of 3. Yep. See, that should be a cube there. Which means that I've made another error. I need to correct that, of course. And I've identified that when I look for the pattern at the end. You see, I know I made an error there. It's easy to make mistakes here. You can be very careful. 4 subtract 3 is 1, raised to the power of 3. This now gives me a negative 27b cubed. Should be here. Negative 27b cubed. So let's fix that. Negative 27b cubed. Now, let's try it again. 4 times 2 is 8 times 27. It's 216. And it's a negative 216. So let's fix this here. It should be a negative 216, a, b cubed, 81b to the 4th. Now I think we're good. Double check. A to the 4th, a cubed, a squared, a to the 1, a to the 0. B to the 0, b to the 1, b to the 2, b to the 3, b to the 4. And again, it's a nice way to check and see if you made a mistake. There will always be a pattern in your powers. It doesn't have to be increasing by 1 and decreasing by 1. But there will always be a excuse me, there will always be a pattern. Nice way to check. Okay, let's have a look at this last one. What is the third term in the expansion? 4b subtract 5 to the power of 6. I'm looking for the third term. By now you should realize the third term is going to be the c of 6 choose 2. And if you don't remember that, then write it out. The c of 6 choose 0 is the first, the c of 6 choose 1 is the second, the c of 6 choose 2 is the third. Your first number is 4b, raised to the power of 6 subtract 2. Remember I told you these two numbers subtracted is your first power. Negative 5 is your second number, raised to the power of, always that number goes right there. Same number goes there each time. Look, 4 subtract 0 is 4, 4 subtract 1 is 3, 4 subtract 2 is 2, 4 subtract 3 is 1. 4 subtract 4 is 0. That number goes there. 0, 1, 2, 3. Should have recognized the error earlier. 4. The c of 6 choose 2. Do it on my calculator. C of 6 choose 2 is 15. So I got 15 times 4b to the 4 times a negative 5 squared is 25. I got 15 times 4 to the power of 4 is 256 times b to the 4 times 25. 25 times 256 times 15. 96,000. There is the third term in the expansion. I didn't have to do it all to figure that out. Okay, come to multiple choice here now. Might be a good idea if we pause it and try this one. This is a nice multiple choice. It's a little bit challenging, but it's a real nice multiple choice for 3200, no question. But again, you might want to try it before you actually listen to me do it. Let's see what it says. The fifth term in the expansion of a plus b to the power of 4, where b is less than 0, is 256. Now, I'm not going to read any more. I'm just going to write what I got. The fifth term in the expansion. The fifth term will be the c of 5, sorry, because we're starting with power of 4. So it will be the c of 4 choose the fifth term will be the C of 4, choose 4. Be careful here. And again, if you need to write that out, you do that. The first term is C of 4, choose 0. 4, choose 1. 4, choose 2. 4, choose 3. 4, choose 4. First, second, third, fourth, fifth term is the C of 4, choose 4. A to the power of 0, B to the power of 4. Again, I got A to the power of 0 because I subtracted my two 4s. That's my first power. And my second power is this number you see here. It says that the fifth term is 256. It is 256. Let's simplify this. The C of 4, choose 4 is 1. A to the 0 is 1. B to the 4 equals 256. B to the 4 equals 256. If I solve that for B by taking the fourth root of 256, it's actually plus or minus the fourth root of 256 because B could be plus or minus here. The fourth root of 256 is going to be, let me just do this here, is really the square root of the square root if you want to do it that way. And I get plus or minus 4. Now I want you to recognize that plus or minus is possible here. Because you're solving this equation. B to the power of 4 equals 256. If B is a positive 4, 4 to the 4 equals 256. And if B is equal to negative 4 to the 4 is also 256. So there are two possible answers for B. But notice, B is less than 0. So if B is less than 0, the only answer that we're looking for is negative 4. So we now know that B is negative 4. It says the second term is negative 433x cubed. What is A in terms of x? So we're looking for A in terms of x. So what I have now is this. I got A plus a negative 4 to the power of 4. Because remember, B is negative 4. The second term is negative 432x cubed. The second term would look like this. The C of 4, choose 1, second term. A to the power of 4 subtract 1, negative 4 to the 1. Because I know that B is negative 4, you see, right there. So I'm looking for the second term of this expansion. Now I already know that B is negative 4, so I've already filled that in, you see. A plus a negative 4 to the power of 4. The second term is this. What are we told with the second term? That equals negative 432x cubed. Let's solve for A in terms of x. The C of 4, choose 1 is 4. A cubed times a negative 4 equals a negative 432x cubed. Negative 16a cubed equals a negative 432x cubed. Divide by negative 16, and I get A cubed equals 27x cubed. So what does A equal? A is equal to the cube root of 27x cubed. I just want to double check. My 432 divided by 16. Yeah, it's 27. The cube root of 27x cubed is 3x. Answer C. The cube root of 27x cubed is 3x. 3x times 3x times 3x is 27x cubed. I've just found the value of A in terms of x. A is equal to 3x. I think we have one more example to do. Here it is, example number 6. And I'm sure you've seen me do this before. Or one like this. So again, you might want to pause the recording and try this one before I actually do it. Last example. What is the 12th term in this expression? The 12th term. The 12th term will be the C of 12, choose 11. The C of 12, choose 11. And I got 2048 to the power of 12 subtract 11 times a negative x over 2 to the power of 11. Remember, you subtract these two numbers to get your first power, And this number here is your second power. That's your second term, negative x over 2. Let's simplify that. The C of 12 choose 11. I'm pretty sure it's 12, but I'm going to double check that. 12 math C of 12 choose 11 is indeed 12. 12 times 2048 to the power of 1 times a negative x to the power of 11 over 2 to the power of 11. 12 times 2048 negative x to the 11 over 2 to the power of 11 is 2048. Those two will cancel, and I'm left with negative 12 x to the 11. Negative 12 x to the 11. The answer is A. Okay, here again is a summary of your key ideas. Pretty much summarizes everything about Pascal's triangle and the binomial theorem. Pascal's triangle has many patterns. Each row begins and ends with a 1. Each number in the interior of any row is the sum of the two numbers to its left and right in the row above. You can use Pascal's triangle or combinations to determine the coefficients of the expansion, x plus y to the power of n, where n is a natural number. So you can use either Pascal's triangle or combinations to expand this. I prefer combinations. I think it's easier, but you can use Pascal's triangle. You can use the binomial theorem to expand any binomial of the form x plus y to the power of n, where n is the natural numbers. It's binomial theorem. You can determine any term of the expansion using a pattern without having to perform the entire expansion, and there's your pattern that we just talked about. The C of n choose k, x to the n subtract k, y to the k. And there's an example of it again. You already saw me do that example. And that ends this lesson.